And I basically just kind of wanted to quickly hop in. I just wanted to quickly just hop into a stream to kind of maybe do a bit of a out loud kind of testing. I don't know. I just, also if anyone's joining and you're interested into knowing a bit more about the details of this idea, the entanglement hypergraph idea, then I'll be happy to answer questions as well, if any. If not, you can watch this offline as well. Uh, Conda activate EHS, and then we'll just go to my simulator notebook for the prototype and open this up. And I'll just quickly actually share this stuff in Twitter, see if anyone's interested in joining. Oh, give me a second. I gotta go open the door. Cool. I'm back in there. See, that's working. That's working. I think so. Yeah. Um, okay, perfect. So what I was saying, did this open at all? Oh yeah, it did open in another tab. There we go. So open this up, and then I'll just quickly drop a tweet that says, so we are feature complete, stream running at twitch.tv uncertain systems. Quantum computing. Why is it so slow? Computing. Okay, perfect. So, cool. Now, first, let me just try to take a step back and try to understand. I'll probably be talking to myself for a while. But if you've got any questions, let me know. If not, you can watch this later and ask questions offline as well. So what is the whole, what is this whole idea for, right? And actually, in the Quantum Daily, if you go to, get the list of articles that I recently published there, there's a bit of an introduction to the concept, and I'm thinking I'll definitely add something to. If you go to uncertain dot systems, uncertain dot systems, there you go. That takes you to my page in StrangeWorks, and I'm going to put something in here as well soon about these. A bit of a more, maybe sort of a version of these as well. So no, I don't. What did I do? Yeah, okay, I think that's the right. Okay, so these are the posts, and that was the first one that I did. I probably should just kind of compile this in a big list or in a big post and then put it somewhere. But anyway, so what I wanted to do today is I wanted to kind of do a bit of a first fly through and fly over sort of testing scenarios or testing cases that I'd like just wanted, to use the tool for, and at the same time have a bit of a random thinking around whether, kind of where to take these in terms of next steps, right? Because this whole idea was born out of the need for so two things, right? So one thing was a need to kind of maybe understand entanglement better and see, see visualize entanglement in a more clear way. And then as a side note, as a byproduct of these, I thought, this might lead into some kind of more efficient representation for a simulator, right? Um, and I'm now like I finished the prototype, and I'm happy because it just confirms that it does what I expected this thing to do. There's a couple of corners to polish, obviously, but it does what this is supposed to do. Should run everything. Yeah, but basically, I kind of thinking about where to take this next, basically, right? Um, and so let me maybe first. It's just going to be an exercise, at least for me, just to kind of walk through, uh, have a bit of a really explain the idea to myself. If you've got any questions, please drop them in chat. I'm more than happy to answer questions if need be. Cool. Let's see, let me just. So let's just start from scratch, right? Where did this whole thing came? Maybe I'll just use Paint and my digital Paint and my digital pen here to express and explain that a bit better. Cool. So, and again, it's just also I'm doing this as an exercise for myself to give me a second because I just spilled coffee. That's not good. That's definitely not good. So I need to get some paper for this. Cool. All good. Okay, so cool. There we go. If you have got any questions, just drop them in the chat as we go on with the explanation. Perfect. Cool. So let's see. Is that working? Yeah, that's working. Cool. So the reason or the idea why these kind of sort of bubbled up in my head as an idea is, I've always had trouble when you have a state vector, right? The state vector formalism tells you, that you basically have, let's say, a 2-qubit system, right? And you start in the 0, 0 state. So you represent this with a cat like this, and basically you evolve the state by applying, the gates, right? Like the Hadamard gate, the X gate, and so you may think, regardless of this is qubit 0, let's assume this qubit 1, and so this is qubit 1, and this is qubit 0, right? So if you have a circuit like this that applies like an X gate, and this is qubit 0, and this is qubit 1, right? And a Hadamard gate here, So what you usually do is you'd evolve these into first like the 0, 1 state, right? That's this X here being applied into qubit 0. And then the Hadamard would basically evolve your system into the 0, 1 state plus 1, 1 state, right? So this is now your whole system. And so another thing you can do is you have, for example, another type of system, right, which you can use, control operations on. And so you have a qubit that you apply a Hadamard gate to, and then you apply a control NOT gate, and that's the typical Bell state, which basically, takes you from the 0, 0 state to the 0, 0 plus 1, 1 state. And I'm omitting here all the complex, coefficients and whatnot, the amplitudes and the phases, just for simplicity. But basically you have these, so you have these set up, right? And it's like, intuitively, especially when you're starting, right? Like I guess when you're getting better at these things, you're better at reading these state vectors, because this is basically a state vector. So if this is A and B, this is your wave function. If this is AB in terms of coefficients, this is AB in terms of coefficients. So the state vector in this case, right? You have a 2-qubit system, so you have basically 4 potential elements, right? So for the 0, 0 element, it's 0 because it's not in the wave function. For the 0, 1 is A, for the 1, 0 is 0, and for the 1, 1 is B, right? So that's kind of the way a really naive simulator would work, is by keeping track of the 4 possible states and evolving them. So you can see that exponentially grows with the amount of qubits, which is why simulators can't just go over a certain amount of qubits. And there are already, of course, smarter ways to, represent that in a more compact way, so you can have more efficient simulations. But whatever, that's the way you usually would look at it, right? But even if you take a look at these and these, right, like there's no quick intuition or intuitive way that tells you, you know, that things are not, whether things are entangled or not. Like you can't easily, like, yeah, if you're getting, if, as I said, as you get good with these, you probably are able to recognize, patterns easily. But usually the recipe to figure out whether it's entanglement or not is, okay, can I express this wave function as a product of the 2 qubits? So can I factor these out, right? In this case, if you've got this here, right, you can actually factor this out, because you can basically take the 1, because the 1 is shared in here. So you can just say, well, it's like me having the 0 and 1 state, and then having this multiplied by the 1 state on, this would be, so this would be qubit 0, right? And this is kind of qubit 1. So you factor this out, and then, these here, I'm so dirty at this, it's basically the plus state. So, essentially you kind of have these. So it's not entangled. Now here you can, because you cannot factor anything out, so it is entangled. But it's, it's like, as this grows, as the system grows, that becomes obviously cumbersome, because you have to figure this out, right? Like whether you can do these or not. And really, I haven't found any tools out there that help you do these. You can also represent systems using a density matrix, but I think I'm not going to get into that, because I don't know enough about it in terms of how much it actually shows you about entanglement directly. But anyway, the whole idea behind this EHS, or entanglement hypergraph project, is to work with a bit of a different representation in mind, right? Say, look, what if we start with a system already as in a representation that is already sort of just the factored version of the system, not the full-blown expanded version of it with all the possible measurement outcomes, but just the single qubit representations. Just keep that, right? Because that scales well. So if you have 100 qubits and you need 100 data points, right? Okay, they're complex numbers, but whatever. You have like just that. And of course, you can't then easily see, for example, what's the probability of measuring a certain outcome out of all these, because you need to compute that, right? Whereas here you see directly, it's like, okay, what's the what's the probability of measuring the one zero element? Well, it's b squared, right? The Born rule, or something like this. Yeah, I think it's b squared. So, and this is how the idea kind of was born, right? In the sense of, you have the qubit system, right? Q0, and we keep track of just the state of Q0, which is in the zero state, and we keep. This is, by the way, the wrong way to say and to do things. It's just I'm going to use the zero state, the number zero, to represent the zero state. That is in reality a complex number. So in reality, a qubit is sort of a it's a two-element array, right? One for the zero component and one for the one component. So in this case, the zero would be basically a one plus, zero I in here, and a zero plus zero. So you're just saying you're saying that this is in the state zero. So that's the technicality here. But I'm just using the shortcut here to say it's the zero state. And so you keep the qubit like these, and then you have the other qubit also in this state. And so far that's it, right? You keep these two numbers in your system, and so now you have to figure out a way to evolve this system, in a way that it does not explode in terms of size, because that's what you want to avoid. So and again, this is sort of thinking through the efficiency, from the efficiency perspective of this whole idea, right? So if you apply single qubit gates, it's easy, right? Because you know that there's nothing is happening. There's no kind of correlations being built. There's no entanglement being built. You can't build entanglement by just applying single qubit operations. So if we had back, let's say the circuit, the Bell state circuit, right? So it's a Hadamard gate in here, and then it's a control node. So the first operation is easy to track, right? Because it's just telling me, please apply a Hadamard to qubit 0. So our system would transition into these, right? So it's still, we have not increased the amount of information we store. It's all the time yeah, okay, 4 complex numbers, right? Like it's all the time 2 times the amount of qubits, right? So for each qubit we have 2 complex numbers. So remember, this is in reality 2 complex numbers, like 1 over the square root of 2 and 1 over the square root of 2 for both components. So it's 2 times. It's not exponential, right? It's 2 times the amount of qubits. And now the problem, now sort of the first challenge appears, which is, okay, how do I represent a control node operation, right? Because this is an operation that can create entanglement, and this is where one has to, this is where basically you can do it the dirty way, or you can do it the sneaky way. The dirty, by dirty I mean brute force, right? So you basically say, okay, cool. So at that point, I know that I have to do that. So I know that this is represented by a mathematically a 4x4 matrix. So all I need to do is temporarily I do the product of those. So I temporarily kind of give up on my space savings, and actually build the the 4-element state vector, and then just multiply by the whole matrix, and then as a result I get another 4-element vector, which I can then kind of replicate back to my node structure by saying, I'm going to have basically my structure is going to evolve now into a hypergraph, where I'm just realizing that there's so much that goes into these that it's complicated to explain even the mental process that's gone through this in terms of why a hypergraph and why would you do it this way. So what I'm saying is, here you have 2 nodes which are independent, right? Maybe I'll try to explain this backwards. The reason the way that you have to think about entanglement is that you have a set of possible outcomes which are just not compatible in terms of you cannot have a mixture of those of those outcomes together, right? So if you have the state 0, 0 plus 1, 1, that's what the state vector is telling you, is that you either will measure these or you will measure these. You will not measure 0, 1 or 1, 0, right? So the way that I thought of representing these in this structure is by basically having a kind of two copies of the system. So you have 4 nodes, right? So you have one node representing 0 and 0. So this is qubit 0 and qubit 1, right? So this is 0, 0 and 1, 1. And so you have a system that actually has all these data points in here. These are related with a hyperedge. The reason it's a hyperedge and not just an edge is because as the system grows and you have 3 qubits, then an edge that connects 2 nodes is not enough. You need to kind of group the 3 nodes. So we keep it general by just talking about hyperedges. And I'm not so sure even if this is the optimal structure to power these, but it's definitely a useful one. So this is sort of a way that you represent entanglement, and this is how you're going to know that your system is entangled. It's because you cannot get rid of these edges. You cannot like factor things out, right? Like if your system doesn't have any hyperedge, it means it's not entangled. Or if it has hyperedges, but then there's a third qubit somewhere that does not belong to any of these, then it means that there's no entanglement between Q2 and any of these, right? But Q0 and Q1 are entangled at the same time. So that's kind of the idea of this. This is just the core concept, right? So you have nodes, and then whenever you come across a controlled operation or a 2-qubit operation, it doesn't have to be a controlled operation. There are also 2-qubit operations which are not controlled operations. Then you'll potentially have to build hyperedges, right? But once you have these hyperedges, you have a really simple structure that you can run a factoring algorithm on, right? So let's imagine that I have a system. I'm not even sure it's going to be correct, but I have a system in this state. So I have 2 hyperedges here, right? That's my system. So I can, because I know that I know I'm drawing this on purpose. I know that these ones are Q0 and this is a Q1, just as a convention. I can think of these. I can think of a strategy to factor these elements out, right? Kind of calculate whether I can factor things out and merge these hyperedges. And because there's exactly one element that is different, right? I can factor out the rest. For me, like I can easily say, look, there's 2 nodes which are the same for the same qubit in the 2 different edges. So these should actually be connected. They should all be one big edge, right? And by virtue of connecting these, then these 2 states, which were kind of mixed in nature, right? It's like it could be either 0 or 1, but it's not that it is the plus state because it's entangled. Now really kind of become the plus state because I'm merging the hyperedge in here. So you would end up, the algorithm basically what this does, right? Like what most of the stuff in here is doing for you is doing this factorization automatically, and we'll take a look at this in a second. But then you would end up with just a system that has one hyperedge that is like that. And if you have just one hyperedge, it's the same as having no hyperedges from that perspective. And so that this is not entangled. So the one way this concept could be used is to you just load a state vector, run the factorization algorithm, and then you get at the end you get whether it's entangled or not. So you have an easy way to see these. Now I could have used, like, why I'm complicating my life with hyperedges and whatnot. I could have used just some traditional factorization algorithm or any other data structure. I think that hypergraphs are really visual in here, and I think they're really helpful to to kind of see that. Also, apart from these, the point is I needed a structure that I can evolve easily programmatically, because the use case here is, remember, it's not only just to say, oh, give me a state vector and I'll turn it into an entanglement hypergraph, and then I can factor things out there. That misses the point, because if I need to get and parse a state vector, I'm already on a losing end in terms of performance, because it means that I have to read like a potentially exponentially big data structure, which is, it's not, I want to be able to have a system that can evolve in an efficient way. So what this does is, as long as there's no controlled operations, it evolves really efficiently. Whenever there's a controlled operation, then it starts to kind of uh, grow. It's sort of the downside of things here, that if you're not careful, you're not gaining anything. Like the more, the more entanglement you have, the more the hyperedge number grows, and actually grows exponentially to the amount of controlled qubits. Because if you if you let's say if you have the Toffoli, if you have, two qubits in the Hadamard, like if you have two qubits in the plus state, and then you apply a Toffoli gate, right? The way this will map into the system is, and actually, because this is an AND condition, you will really have to have four hyperedges, right? The hyperedge 0, 0, 0, 0, 1, 0, 1, 0, 0, and then 1, 1, 1. So this is the only place where we apply the actual target operation, because the two controls are in one. So, and these all get wrapped into hyperedges. Oh, thanks for the nice comments. These all end up in hyperedges, and as you can see now, we've had basically two control qubits, and so we have like four edges, four hyperedges. So our structure actually does grow exponentially, and that's not good. Now I'm currently working on, from a prototype perspective, that's fine. It's something that, like, okay, so I can simulate low entanglement circuits efficiently, like 1,000 qubits, 5,000 qubits is no problem. But as long as, like, if you have Grover's algorithm that creates an entanglement, like it creates a controlled operation across the entire um, set of qubits, like, then it just explodes, because it has like a huge control Z in the middle of the diffusion operator, and that just explodes, right? But I believe there's a more efficient way to um, evolve these, but this is kind of going to be post prototype, right? So, because if you pay attention, there's some sort of symmetry here, as in, like, to be honest, I only need to keep track of, kind of this branch potentially. I don't need these. As long as I store some information in here that tells me that, hey, there's all the branches in here. Maybe I can keep the branch as in like these, right? Um, and then keep two nodes in here somehow, right? That tells me, somehow this is a branch that it's compressed. And as long as I don't, clash with another operation that is going to then modify something from some of these uncompressed branches, which then I can probably carve out from here. There's going to be a smarter way to do these, but I think there's something you can improve there. But from a prototype perspective, that's all kind of fine. Um, I just, it's nice because you see the entanglement, like you see what are the values that are entangled, and you can easily say, if I measure this qubit, 1 to be 1, it means these hyperedges don't exist anymore, and so my system is now, only made of these two hyperedges. So I think it makes analysis more interesting, and it's visual in terms of, the type of entanglement that you have, and it's a great tool to explain phase kickback, which I'll do now in a second. Okay, so I'm not making anyone look down. Come on, people. That's not. It's just I've been thinking too much about this stuff. If you spend enough time thinking about things like these, then you end up just looking like smart, but not that really. Mm. So phase kickback is a concept that a lot of people struggle with, because it's not obvious, right? Let's open Quirk and see it in action. So what phase kickback is, the effect that happens when you have a system like that, right? Where two qubits are in the plus state. And now you apply a control, sorry, one is in the minus state. This is better. So this is in the minus state. And now you apply a control X. And you see what happened? So actually, this state hasn't changed, but the control state has changed. Like, it used to be a plus, and it's a minus after the controlled operation, which is super counterintuitive, because you're like, dude, I just did a control. Like, how it goes against classical intuition, where one would think of this, okay, this is a, if it's one, then apply this operation, but if it's not one, then don't apply this, and yeah, sure, that creates a superposition and whatnot, but how the hell is that supposed to turn my state from a plus to a minus, right? Because that actually has an important effect, which is if I now hotmark the thing, then I'm not back at 0 anymore. I'm back at 1. I'm actually at 1. So this is a concept that I myself struggled a lot to understand. And these type of entanglement hypergraph helps you in visualizing these in a neat way, which again, I'm not claiming you cannot visualize as any other hat. Like you can probably take just a wave function in Git notation and do the same, but it's just a bit more mathy and cumbersome, and it feels like the hypergraph version of it is a bit more clear. So let's actually replicate these, right? So we have qubit 0 and qubit 1, right? And we start in the 0 state, and in the 0 state, then we apply a NOT gate here. So that turns into, I'm gonna split the system like this. So now we're in the 0 and the 1 state. So far, so good, no entanglement. And again, we're very being more efficient because we have only 2 qubit data points we're keeping track instead of 4, right? Now come to Hadamard gates. And so we turn this into the plus state and this into the minus state. I can also write these things for simplicity as a 0 plus 1, 0 minus 1. I mean, not simplicity. This is a simpler way of seeing things, but this is going to help us see the phase kickback effect. So this is my current system. And I'm omitting here, again, all the complex numbers that are associated with these things. But they are there in the simulator. So this is what we have. And now, an intuitive way to think about a control knot with this type of structure is that you don't have to actually do a math multiplication. You can actually think of this in a really dumb, basic, classical way and say, look, the control is now going to split my hypergraph into 2 hyperedges, because here I have a 0 plus 1, but I'm trying to force the thing to apply a condition only when it's 1, but it's not only 1, it's 0 and 1 at the same time. So a rule for a control knot would be, now I split this thing in 2, right? And then I modify this state accordingly. So this is going to give me 2 hyperedges. One hyperedge is going to have a 0 node, and it's going to have a 0 minus 1, because I'm going to leave this state untouched. And another hyperedge, and I'm marking it now with a stripe because it's just easier, because it's 2 nodes, right? But usually I would wrap it up in a circle or something. So now you have like a 1 here, but now you apply an X gate, right? An X gate, remember what it does is it turns a 0 into a 1 and a 1 into a 0. So it really will turn these into this state, which, if you're a bit familiar with quantum stuff, you know that these states are physically equivalent, right? Because the 0 minus 1 and the minus 0 plus 1, they all have its relative phase. So what counts is the relative phase of the 1 component towards the 0 component, and in both cases it's like 180 degrees. So they are all equivalent, but mathematically we've ended up with something that is mathematically not equivalent, right? So we know from an experimental perspective that these things should be equal. And here's when the phase kickback becomes visible, right? Because now the question is, I have this system. So how do I want to factor these out? I want to factor things out to see if this system is entangled or not. And okay, I can cheat a bit because I know it's not entangled, because I mean, for such a small system, I can check it with Quirk, and I can see that it's not entangled, right? Both values are independent. Oops. But I pay attention that, like, it bothers me the fact that there's a global phase. You can think of these as, these having a global phase, right? It has a global phase of 180 degrees, which, for the sake of manipulating the structure, you want to get rid of, because you want to make sure you can compare things at the physical level and say, is this state physically equivalent to these other states, so I can check whether I can factor them out. So one of the things that the factorization algorithm does is it first runs through all the branches, all the hyperedges, and removes the global phases. But you cannot just remove the global phase. You have to put the global phase somewhere else. And what this algorithm does is it puts the global phase at the hyperedge level. The reason is that the hyperedges are, at the end of the day, translated to specific components in your wave function, and these components will have a its own complex amplitude. And so this is something you can do. I have a couple of videos that go a bit more in detail on how I've figured these out, but it's probably too much in detail for now. But the idea is that this system turns into the system like, you know, this hyperedge stays the same, but then this one gets corrected. So these two, so this is, it's basically turned into the convention of the zero component is going to always have, no phase. But now you have a like 180 degrees phase, right, which is like a -1 from a sort of mathematical perspective in terms of the because it's a complex amplitude, so it's like 180 degrees in the complex plane would be a -1, and that now sort of belongs to the hyperedge. The reason this can belong to the hyperedge is because in theory, I don't care what element has these. All I care is that when I want it, if I want to ever translate that into the state vector, I'm going to have to do the product of these. So I'm going to have to do like the the minus times 1, right? And I don't care where this -1 sign is, because it's going to end up at the front anyway. So it can just stay at the hyperedge level. And now I can make a comparison, because now I can say, good, are these elements equal? Can I factor things out? Well, yes, you can. So this element and this element, now they are equal. They are both a minus, so I can factor them out. So, you could think of these being sort of as an in-between step, which is not, doesn't make much sense, but it's just to illustrate these. You're connecting this element, but now you need to connect these two, right? And in order to connect them in a way that is consistent with the mathematical formalism behind state vectors and whatnot, if there's any complex amplitude associated to an edge, it needs to be taken down to that element, right? Because now you're going to make a pure state out of a mixed state. So this -1 now comes here. And guess what? You end up with 0, -1, and 0, -1 system, totally unentangled. And this is the minus state, and this is the minus state. And voila, that is actually phase kickback. So it kind of, we've moved from a plus state to a minus state. And sorry for the mess in here, just by virtue of running the factoring algorithm, right? So it's what this system is, supposed to make, make it easy for you to understand how, how these kind of things happen. So I think this idea is going to have, or it definitely has, some kind of educational component to it, that at least programmatically it lets you manipulate states in a way that you can see things like these happen. While developing that, I also kind of learned a couple of interesting tricks around things you can do to collapse, to create superpositions and stuff like that. But I'll leave this for another stream. Let's play a little bit, because I'm taking a look at the time, and I think gonna have max like 15, 20 minutes more for these. Again, if you have any questions, feel free to reach out. Like, I've got the, if you don't know, I've got a YouTube channel where I'm archiving all these videos. You can reach out via Twitch as well, the chat, or also I've recently purchased the uncertain.systems domain, which I'm really happy. And you can just reach me at, shoot me an email at daniel@uncertain.systems. In case you wanna, I'll just put it in the chat, in case you wanna reach out and wanna play with these. This is available in GitHub, by the way. So it's still really, it's a prototype, right? I think it's a nice idea, sort of both ways, as I said, from a simulation perspective, because I believe there's potential to have, more efficient simulations, but also from an educational perspective, and just as a tool to manipulate a system in a way that you can kind of maybe, design an algorithm or try to figure out, how to implement a certain trick. I definitely want to move away from just talking qubits and also talking like, actual numbers. For example, if you so in the Quantum Daily, if you go into Quantum Daily, I have a series of articles that explain that in a bit of a more structured way. I have to link them all still, but they all contain links to actual archived videos on, me building that stuff. But you have, for example, sort of what I just explained now. Uh, sort of the initial state, and here I have a bit of a nicer notation for that, and kind of, I take you through the process of how to implement a control knot, and things like these, right? So I think it's, and I'm definitely going to make a more polished version of these and make it public out there. But let's play with these. Now I have it basically feature complete. I have the prototype feature complete in the sense that you can apply one qubit operations as long as you have the matrix. So for the one qubit operations, I do revert to, I do rely on the actual matrix multiplication because I think it's just convenient. I might change that because ideally, if you think about the fact that you have a hypergraph, maybe you can think about the formalism actually being more around um, transformations and how you can transform the hypergraph rather than just multiplying things around. But because it's just a qubit isolated operation, these, for operations like the X gate, the Z gate, the Hadamard gate, I just rely on these. And then I have two methods that implement. So I have a method that implements two qubit gates, and it's also using the. To be honest, this is a bit of a cheating. It's not cheating, but it goes, it follows the non-optimal approach that I described before. So it actually uses the metrics as well. But I have it there just so I can also run non-traditional, non-control style gates, right? For the controlled operations, I have a specific operation that it's, I think, a little bit more efficient. Probably not because I'm expanding it anyway, but this is a place where I can definitely make it more efficient, where you provide the controls, like any number of controls, the target, and then what is the gate you want to apply to the target, and it's going to apply the by default, like the, you know, um, all ones type of end controls, controlled operation. Um, so the way this works is like this. Let me just think we're done with paint now. The way this works is like the following. So you load the whole thing. And again, this is just a prototype, right? So these first two cells contain the bulk of things. So, and I'm really not happy with the names and whatnot, right? But you have, let me start from scratch actually. So what you do is you create a system by creating a hypergraph, right? So system equals hypergraph, and you give it the amount of qubits that you want. I will initialize this by default to 0 yeah, I'll call the system mass. It's going to be easier. If you do these, what this also prototype does is it draws the hypergraph. It draws it in a way that at least guarantees that it's readable, because you can do this in a rubber band style where you kind of wrap things around circles, but then I realized as the amount of qubits grow, it just becomes unreadable. And I am definitely moving into a more friendly representation of these, but this was just a working example. So you see that you have the qubit 0. It's in the, and this is again, this is the, real underlying data structure for the qubit. It's the qubit state. So it's 100% on the 0. And it's 100% on the 0 state as well here. So both qubits are in the 0 state, and they are all belonging to one hyperedge called system. The reason is the visualization library that I was using, that I've been using, doesn't allow for some reason to have no hyperedges, and so I had to kind of make up the system one, which basically means they're not entangled. So this is, you can have 3 qubits, and you have 3, and as I say, you can have 3,000 qubits, right? That shouldn't be a problem. It takes a while because it just needs to render these. So I think it's more inefficient on the visualization side here than on the actual computation side. And I hope I didn't just break things now. But that's oh God, I should have put the lower number. It's definitely the painting that's, can I just delete that? What if I delete the cell? Delete the cell and all your problems will go. Hypergraph, say 10, draw. Oh God, I think the process probably kept running. So I think I might just have to restart the kernel and run everything. Let's see if that works. Yeah, there you go. So it's 10, 10 qubits. Again, it's not perfect. The ordering is just messed up. It should go from 0 to 9 and whatnot, and it takes too much just to paint this picture. So I'll just keep this small anyway for the sake of these stream. And I wanted to do some testing, but I'll probably do another stream tomorrow where I'll really focus on actually hands-on testing these. But the idea is that you can evolve the system by just saying, hey, apply. Oh, actually, I think I got a, yeah, did I actually integrate it here? Yeah, there's this function that was basically sort of a result of a pull request by someone from the Discord server. Thanks a lot for these. Where it kind of allows me to apply to not specify these, but I'm I'm sorry, I'm just gonna keep using the other ones for now. So whatever, I can just do it like that. Probably that's gonna probably work anyway. So I think I think that's the way it works, right? So yeah. You know what? I'll just. Oh no, it's okay. I know. It's just comma separated, so I can just say Q0 and then. Yeah, so you can see that for qubit 0, I don't know if you can see this, it's changed and now it's in the 1 state, right? Before there was a 1 here. I don't know if it's too small. Hopefully it's not too small. And now it's a 1 state. So this is the X gate. I can also, apply Hadamard gate instead, and it basically, yeah, you see now it flipped the ordering. Now the Q0 is at the top, before it was in the bottom, so it's a bit confusing, but that's why I keep the labels in here visible. The visualization is just crappy, but it evolves the state like that. And what's interesting is when you now apply, what's wrong with my typing today? I apply I can apply a control gate like this, or I can apply it with the controlled operation, right? So if I do this, now what you can see is that we've created these two. Do I still have it on Paint? No, that's already the other example. Anyway, so let's write that example so you can see that actually works, and at least in terms of the phase kickback. So you can see that now, things are like that. And so you have the two branches. This is one branch, and as you can see, it also has this complex number here because it's something that we factored out from these two. And you have the 1, 1 and the 0, 0 hyperedges, right? And what you can do here is also factor qubits, right? For now, this works really naively, where you have to give it all the qubits. Like, if they're entangled, that's the problem. You just have to give a list of all the qubits. I'll improve that. It's just a prototype. But what this does is it tries to factor things out, in which case it just won't be able to, so you end up with the same system, right? If we had and actually in theory can even give it the steps. So if the factorization is a multi-step factorization, because it does edge by edge comparison, you will be able to go and walk through each of the steps, so you can see things like the phase kickback happening, right? But let's do the example. So let's do the example that we just did now in Paint. So first, so to qubit 1, we apply an X gate. To qubit 0, we apply Hadamard gate. We apply another Hadamard gate to Q1, and then we apply a what do we have? A control X gate. So we end up, as you can see, you end up with 4 different hyperedges because it's not factorized yet, right? Again, I know that's highly inefficient. That's not the point, right? Like, it's exploding exponentially, but it's just a prototype. So I'm gonna be working on sort of transformation rules that allow you to run controlled operations in a more efficient way, so we don't expand to the full set of correlations. But now I can try to factor things out because I know I run it in Queric and I know that this is not entangled. So I should be able to factor things out and end up with a minus state. And I hope that doesn't leave me now in a stupid. So this should work. Let's see. So it does all the factoring stuff, and boom, you end up with a system that's now it's it's unentangled, right? So you have no hyper edge, just the system one. And I don't know if you can see the little minus here. So this is the minus state and this is the minus state for both qubits. So it basically actually works. So that's what we end up with. It works at least for this case, right? Um, yeah. Again, you can run. You can also apply the controlled operation is controls target and gate. So I can also, the equivalent would be that I would say, these are the controls, this is the target, and it's the next gate. So this is another way, because it's going to be, otherwise you cannot implement something like a Toffoli gate, right? So, this should actually lead to the same outcome possibly. Yeah, cool. So this is another way, and this is what's going to allow me to hook up a bit of put in a bit of efficiency in terms of how this is run. Mm. But kind of that's really the Roth idea, right? And it's feature complete in the sense that you can also measure qubits. So now let's say we have a minus minus system, right? In Quirk you can go and say, look, I wanna measure these, right? What this does is that actually assumes the measurement is deferred, so it puts this qubit into a classical state of it's either 0 or 1, right? And it still gives you the state vector, assuming that you haven't measured yet, but that's the idea. That's what a measurement does, is it destroys the coherence, it destroys the quantumness of the state, and it's now either 0 or 1, right? And you can also do pos selection, which is basically what it does is it measures and it then just keeps the zeros. And this is also supported in here. So you can also just say, even after factoring, before factoring, whatever, but let's do it after factoring. So I can also say as measure, and I think I have to give it a list of qubits, and I say just measure qubit 0. So what you see now is that actually we went from a non-entangled system to something that looks like an entangled system. And it's really cool to see this because it actually kind of tells you that entanglement and measurement do have a lot of similarities. And you can see that now the qubit 0 has this little m here, which means this qubit has been measured. What this means is the system, you cannot mix them up again. I cannot apply Hadamard to these qubits because they are now collapsed, right? So they're not quantum anymore. But you still have the whole structure, and so you can still reconstruct the state vector out of these because you have all the numbers, all the probabilities and whatnot, and you can just multiply things and get the state vector as if you hadn't measured yet. But that's the idea. And so, basically, you can see you cannot merge them, right? Because they are measured. And you can also do is pos select, and I forgot what that looked like. Is it pos select Z? So pos select would just measure and select stuff in the 0 state by default. So I can replace that with a pos select, and what it will do, or what it should do, is it just keeps one of the branches, right? It keeps one of the branches, and I just spotted the back. That should definitely not be an edge. It should be the system edge. So that's definitely a back, something to fix. But it dropped the other branch, right? So basically, you kind of see that, it's feature complete from that perspective. Yeah, basically that's it, really. I'm bad at explaining stuff. I'm really bad at explaining stuff, so I hope that was somehow understandable. I was just kind of quite happy to. I haven't gotten, because I don't have much time to work on this stuff, with a day job and a bunch of other obligations. It's always complicated, but at least the prototype now, I'm convinced that this is somehow doable and it is to some extent useful. So yeah, I'll do another stream tomorrow probably, or in 2 days. I'll see. It depends on my time. Where I'll really get to actually do some testing. And the testing will really just be me kind of running through different circuits and comparing the state vectors at the end, and then seeing if there's any flaw. I know for sure the factorization doesn't fully, there's something it's not fully, it's not really well rounded up. It works, but it's not like, as you can see, like it did now, it didn't now work as I expected it, where it would just leave this in the system edge. It just kept an edge, which makes no sense, because this one component here makes no, I mean, it makes sense mathematically, but it's just not how I liked it. I'd like to have it just as a system. Um, yeah, and basically, so this is it, right? So it's a bit of an educational tool. So I think the factorization stuff here, I think I can also you can also add the steps, as I said, and if it's it kind of walks you through the step, it merges branch by branch, and so you can see what a thing's happening and how is phase kickback happening when you're factoring things out. So there's, an educational component of it that I could explore. There's an efficiency component of it that I could explore with it. Um, I don't know. We'll see. My plans would be to turn that into somewhat like a more robust and actual library that you can work with. Um, Maybe integrated with Quirk. I don't know. Like maybe, kind of be able to have a display here where you see these branches somehow in a hypergraph way, nicely laid out, so you can see the correlations. But I don't really know. It was an exercise, at least from my side, to kind of learn more about how systems behave without thinking too much about the state vector formalism. Um, and at least it opened up, my eyes in terms of how you can interpret controlled operations, as in like edge creation or edge splitting transformations of the hypergraph, which I believe kind of can lead to a bit of an efficiency gain in terms of simulation. But I don't know. At some point things just will explode, right? If you need to modify something that you've got compressed, then you got to uncompress this, and that's when things go south. But the same with MPS, which is the matrix product state model, which is also a compact way of evolving a system, has the same flaw, right? Like if entanglement grows, then your tensor network will also not be as efficient as you'd usually expect it to be. But anyway, cool. I hope that was interesting. I really wanted to do this as an exercise for myself as well, to kind of, take a step back now that I was sort of feature complete, and think through, okay, what is in here and how can this be useful? It was useful for me in a bit of a, uh, uh, you know, um, selfish way to learn a bit more about stuff and how you implement things like this. And yeah, I don't know if to take it, down the educational route. I Then you want to have, which is probably what I'll do. I think sort of an educational tool slash maybe a sort of a bit of a debugging tool, or a bit of a, because think about these. If you think about not Grover's, Shor's algorithm, it could be if you move away from qubits and you end up you work at the register level, so your nodes actually have decimal numbers, for example, instead of just qubits. Um, you could kind of play with a toy version of Shor and see how the algorithm really exploits entanglement for these to achieve its outcome, right? So it's got a bit of an educational slash development tool kind of, or prototyping tool, maybe prototyping tool type of vibe that I'd like to maybe capture in a way that it's useful for someone actually trying to build a quantum algorithm, which is break an actual algorithm down in a way that you don't have to do all the math, like factoring things out and stuff like this. This allows you to do it in a programmatic way, which is yeah, from that perspective, it would be even nicer here. But the problem with Quirk is Quirk really stays at the qubit at the Quirk really stays at the qubit level. It doesn't go at the register level. In a way, I mean, it does, to be honest. It does, because you can have the input gates and all that stuff. I don't know. I need to reevaluate that a little bit, but yeah, I think that's and I also worked on a cytoescape export, which is basically exporting this whole thing into a big JSON thing. It dumps it into a JSON string, so you can then, because I'm playing with JS based visualizations of hypergraphs, which are nicer. um, we'll see if that goes into a tool in and of itself, something like Quirk. You know, um, I'd like it to have integrated to Quirk. I think because Quirk is awesome. Just basically the flexibility you have here is just awesome. So if I would just have an entanglement hypergraph display, it's probably what makes a lot of sense. It wouldn't be for efficiency perspective, but it would be it would definitely be for an educational or sort of a debugging perspective, and you would kind of be able to have a display here and actually even step through the factorization. Yeah, I think that's that's what makes more sense. That's what's worth investing the time in. And even if Craig does not like kind of maybe like it as a an additional to the tool, I'll at least have it for myself and maybe offer sort of a quirk version that actually has this gate available through the site. But that's probably yeah, that's probably the best way to go about this. And yeah, because with these you can like with quirk you can build cool. You can also build, as I said, right? Like in Play with Shore at the register level, I like the fact that you can do things like these and actually, yeah, that's something you can't usually do with. So this, with all the simulators, and it's just so quick and intuitive to work with. So you can have the modular exponentiation part in here, blah, blah, blah. Like you can build something quick. Maybe, you know what? Yeah, I think maybe there's a way to have register displays as well. Well, at the end of the day, it's these, right? But you have here the elements. Doesn't matter. I think it doesn't matter. It really doesn't matter because here you already have it says decimal 0, decimal 1, decimal 2, so it's good enough. That's definitely good enough. Yeah, that'll probably be the best next step, I think. So to put this into Quirk, and yeah, so I need to have a nice visualization that actually maps with this one, uh, with a style at least here, and because yeah, you can. I'm not so much interested in the efficiency component of these. So anyway, we'll see. It's just a personal interest perspective. I'm less interested about efficient simulations because I know eventually a quantum computer will just beat any simulation, or at least that's my feeling. Um, it's more about the educational component of it. And I think no matter what algorithm you want to build, there's always a small version of it you can build and to test stuff out. So I think it's not a big deal where like, oh yeah, I need these algorithm, whatever, to prove that stuff. Like, I think there's always a way you can just build a small version of it. Maybe not, but who knows? Anyway, I hope you enjoyed the stream. And see you next time. Bye bye.